everyone. Today we're going to be going over acids and bases for our AP Chem review. One of the harder units for sure. So let's talk about the definitions first of all. This column's for acids, this column's for bases. By Arrhenius defined an acid as an H plus donor and a base as an OH minus donor. Brownstedt-Larry, which is the most definition you'll need the most, it'll say an acid is an H plus donor and a base is an H plus acceptor. We'll talk in a sec why that's more general and helpful. Lewis defined things in terms of electrons. He said an acid is an electron acceptor and a base is an electron donor. Lewis is the hardest one to remember. The way I like to remember Lewis acids and bases is if an acid is an H plus donor and you're donating like a positive charge, it's the same thing as accepting a negative charge. And then likewise with base, if you're accepting a positive charge, it's like you're donating a negative charge. So H plus donor becomes E acceptor and H plus acceptor becomes E donor. That's how I like to remember Lewis. Our strong acids are 3 halides except for F, so HCl, HBr, HI, and then HNO3, H2SO4, HClO4. It's important to remember that H2SO4 is a strong acid, but once it loses that H and becomes an HSO4-, that's a weak acid. Strong base is any group 1 or 2 metal with OH-, so anything in your first 2 columns with a hydroxide is going to be a strong base. What's good about strong acids and bases is the reaction is very straightforward. It's a one-way arrow. So if I wanted to write the reaction for HI, it would simply be H plus I minus. And if I wanted to write a reaction between a strong acid and a strong base, so HI plus KOH, which is a strong base because this is in group 1, is going to form, doing our double replacement rule of our outsides and our insides going together, water and Ki. This is a common trend. Whenever you have a strong acid, strong base reaction, what you're going to form is water and a salt, always. So the reason a Lewis acid is important is because it defines reactions like this to be acid-base, even though they don't look like acid-base. So this is a common MCQ in the AP. They could give you this and say which is the Lewis acid or base. So the first step you do is draw out your Lewis structure, Lewis dot structure like this. And almost always these questions will have one of these elements, which we like to call B-ball. What a B-ball element is, it is an element comfortable with less than 8 electrons in its octet. So for beryllium it's 4 and for these two it's 6. These elements are okay with less than 8. So when you draw their Lewis dot structure, it will often reflect that. So here, boron has 6 electrons, meaning that it has space for one more if it wants. And if we draw NH3, there is a lone pair right here. So this lone pair can go over here and form a bond between these two. Now this is an acid base because here we have an electrons being donated, so that corresponds with a Lewis base, electron donor. And then here this is accepting electrons, which is a Lewis acid. So that's how you figure out Lewis acids bases when given this. These equations are all given on your sheet, but you should be comfortable with them off the top of your head. You don't need to look for them. This one's not given, and you should know this for sure. pH plus POH equals 14. So if we have one of them, we can get the other. This will be used in hydrolysis in a sec. As a sample calculation, if we have 0.10 molar of HCl, it's going to fully dissociate and form 0.10 molar of H+, meaning that we can take the negative log of 0.10, which is the negative log of the H+ concentration, and get pH, which is 1. For Sig Figs, note that this initial value has 2 Sig Figs, and then for pH, our Sig Figs count after the decimal place. So even though this looks like 3 Sig Figs total, it only counts after the decimal place, so it's 2 Sig Figs, so we're good. With weak acids and bases, a weak acid is literally any other acid that's not the 6 we talked about. A weak base will usually have N or be an organic compound with N. With weak bases, when you write the reaction, you'll need to include H2O. Because notice how when you add H2O, it will form its conjugate acid right here. And then, of course, the base will produce OH-. To produce OH-, you need an O on your reactants. So without H2O, the equation doesn't really make sense. So remember, with weak bases, you always include water in your reaction. For weak acids and bases, it's a straightforward equilibrium calculation. You should be comfortable with equilibrium before you even touch acids bases. So if we start off with 0.10 molar of HF, for example, it's just going to be ice chart. So initial change in equilibrium, 0.10 starts, and then 0 and 0 starting concentrations of these, minus X plus X plus X. Now this final thing should be 0.10 minus X. But if you remember from our equilibrium unit that if your K value is less than 10 to the negative 3, so if it's like 10 to the negative 4 or 5 or more, then we're able to pretty much always ignore this minus X or plus X anywhere. So on your FRQ, I would write like by 5% rule and cross it out. You don't have to like actually show the 5% rule, I'd assume, but I would definitely write it so they know they know that you know what you're doing. Following this, you just multiply your products together at the top over your reactants. Again, this is equilibrium. If you have trouble with equilibrium, catch up on that first and set it equal to our Ka. And solving for x in this, I get the x is 0.0082. So that's the concentration of H. So if I want to get pH, I'm just going to do negative log of this x value. And then I get the pH is 2.08, noting that 2 sig figs are after the decimal place because we have 2 sig figs initially. Let's talk about polyprotic acids. Polyprotic acids are acids with more than one H. So most commonly, there's H3PO4. With these equations, with these reactions, you'll be given more than one K value, Ka1, 2, maybe 3. Those correspond to your first dissociation and your second. So the only difference with this, let's say we start off with 0.10 molar of H3PO4. We're still going to do our ice chart as an equilibrium calculation. So if we have 0.20, these will start off at 0, 0, and then minus x plus x plus x. Since our K value is 10 to the negative 5, we can pretty much assume this negative x goes away by 5% rule. And then this will end up being x and x. So our equilibrium will be x squared over 0.20 equals our K value, which is this. So I could solve for x in my calculator now. And when I do so, I get about, with 2 sig figs, 0.0029. So now 0.0029 is our concentration of H and of H2PO4 minus. So H2PO4 minus is still an acid, so I can do this whole process again with another equilibrium chart. But note that this is a common mistake. Our initial value for H2PO4 will be what we just solved, 0.0029. However, our H plus concentration will not be 0. It will also be 0.029 because in our last ice chart, both of these are x. So H and H2PO4 are both this value that we solved. This is 0. So we'll do minus x plus x plus x. Our minus and plus x's go away because our K value is 10 to the negative 8. So this is going to be 0.029, 0.0029, and x. So setting up our equilibrium, it's going to be our products multiplied together over our reactants equals our second, or Ka2 value from up here. Notice these will cancel out and we get that x each equals Ka2. Now you can't really put on the AP just x equals Ka2 because it's not really a law, but I would use this to check my calculations after I work for a bit. And then solving for x, I would get my concentration for HPO4 2 minus, and I could do this whole process again with a Ka3 in the same exact way and solve for our PO4 3 minus concentration. Note that calculating the pH of a polyprotic acid is only based on the first step. Don't waste your time doing other steps. You can just use the first step because any other contributions from these other acids that form are so insignificant that they don't really contribute to the pH. So if it asks for the pH of a polyprotic acid, you can only do the first step and do this. And you can write any other contribution from later acids do not contribute noticeably. Moving on to hydrolysis. Hydrolysis will give you, they'll give you like a salt, or they could straight up give you a conjugate base. So let's do a calculation with like 0.050. Now here, let's do it with, if they give you Kf, that means we're going to use F minus. I'll get to in a sec why the K doesn't matter. But F minus is the conjugate base of an acid. So as a quick review, a conjugate acid, conjugate base, if I have an acid like HF, its conjugate base is going to be F minus. In other words, after it loses its H. If we had KOH, for example, its conjugate acid would technically be K plus, even though you don't really have to worry about conjugate acids for strong acids and bases. But a better example would be NH3. Its conjugate acid would be NH4 plus. So notice here we have the conjugate base of HF. So it's going to behave as a base. So a weak base, again, will need water, as we talked about earlier. And then this will form HF plus OH minus. And now we'll run through our same calculations. H2O will not matter in our ice chart because it's a liquid. Again, refer to equilibrium for that. These will be 0. This will be minus x. This will end up being 0.050. We can ignore the minus x by 5% rule because our K value is 10 to the negative 4. This will be plus x, so this will be x. So setting up our equilibrium, it'll be x squared, our products multiplied together, over 0.050. equals, now it's not equal to Ka, because Ka is our acid equilibrium. This is now behaving as a base, so we have to use this relationship. Ka times Kb equals Kw. So what we want now is Kb, because it's behaving as a base. So Kb is going to be equal to Kw over Ka. I get that just by dividing Ka on both sides. So now in our equilibrium, it's not going to be Ka over here, it's going to be Kw over Ka. What the heck is Kw? Kw is 1.0 times 10 to the negative 14. And yes, with two Sig Figs. 1.0 times 10 to the negative 14. This is given on your reference sheet, but again, you should know off the top of your head so you don't waste time. So now solving for my x, I'll get over 6.8 times 10 to the negative 4. About x equals about 8.6 times 10 to the negative 7. Let me just make sure this is all good. Yeah. So notice how x here is going to be our OH minus concentration. So if I take the negative log of x, that's going to be POH, because it's the negative log of our OH minus concentration. So negative log of that will give me a POH of about 6.07. So to solve for my pH, I know that POH plus pH equals 14. So that means 14 minus POH equals pH. So 14 minus this value right here should get me my pH. And I get my pH is about 7.93, which makes perfect sense because it's behaving as a base. Moving on to pH of salts. So this is a conceptual type of problem where they'll give you a salt and they'll say, is this, what's the pH of it? Is it acidic, basic, or 7? So Kf, for example, or actually let's start off with NaCl. Na plus comes from NaOH, a strong base, and Cl minus comes from HCl, which is a strong acid. So if your two things in the salt come from a strong acid, strong base, then its pH is going to be 7, neutral. Oh, I drew it in the wrong spot. Then its pH is going to be 7. Now let's say I had Kf instead. K indeed comes from KOH, which is a strong base. However, F comes from HF, which is a weak acid. So basically, if something coming from a strong base and a weak acid, so strong base, weak acid, it's going to be basic. And now in the other way, if I have NH4, NH4 plus comes from NH3, which is a weak base, and then Br comes from HBr, which is a weak acid. I mean a strong acid. So I have something from a strong acid and a weak base, so this is going to be acidic. So that's kind of the rule of thumb. If it comes from strong acid, it's acidic. Strong acid, weak base, it's acidic. Strong base, weak acid, it's basic. And then strong, strong, it's neutral. Weak, weak, you'll never get. So that's kind of the rule of thumb. The actual reason is because, let's use Kf as an example. F minus is going to perform the hydrolysis we just did up here. F minus is going to act as a base and form a little bit of OH minus. We literally got the pH to be acidic at 7.93. However, K plus is going to do nothing. And that's because it comes from a strong base. And remember, bases are a one-way error. KOH is going to form K plus and OH minus. This is one way. It's never going to go the other way. So K plus will never go backwards. It doesn't have hydrolysis. It's not going to be acidic. So that's the actual reason behind it. But as a rule of thumb, whatever is strong, it'll probably be that. Unless you have both of them strong, then it'll be neutral. Let's talk about buffers. What a buffer does is it maintains a pH relatively at one spot. So what it is it'll have an acid or a base and its conjugate. So as an example, this is a very basic example, we could be given acetic acid at 0.20 molar and acetate at 0.15 molar. So to solve for the pH of this, again, it's an equilibrium calculation, except now instead of this starting at 0, it's going to start at what we're given here. So these are our initials, minus x plus x plus x. Our minus x's and our plus x's go away by 5% rule because our K value is 10 to the negative 5. So setting up our equilibrium, it'll be 0.15 times x over 0.20. equals our Ka value. So I could solve for x right now, and it'll be, our Ka value is up here for your info. So solving for x, I get about 2.4 times 10 to the negative 5. So 2.4 times 10 to the negative 5 is going to be our concentration of H+. So getting the pH of our buffer solution is not that difficult. We found the concentration of H+ as we always did, except updating our initial, and the negative log our H+ concentration will give me my pH. So if I negative log that answer and keep my Sig Figs, I will get about 4.62, which makes sense because this is, at the end of the day, a weak acid. Now let's see a whole point of a buffer. A buffer is meant to resist changes. Even if you add a little bit of H+ or OH-, it should stay around the same pH. So let's add now 0.10 molar of HCl. So adding HCl, that's basically adding H+. We have two things in our buffer, and each one is meant to reduce a certain change. So if I'm adding H+, it's going to react with the acetate, and it'll form this. Now think about it. If I added instead OH-, it's going to instead react with our acetic acid, like this, and it'll form H2O plus acetate. So whenever you add something to a buffer, whenever you add H+ or OH-, it will form the other thing. So what I mean by that, if I add H+, then it'll react with this conjugate base and form the acid, and the other way around. So this makes more sense with practice, of course. But let's say I added 0.10 molar of H+. This is now a limiting reagent. It's one way. It's one way and not equilibrium, because H+ is very reactive. It's going to react right away with this stuff. So when it reacts with our currently 0.15 molar of acetate from up here initially, this acetic acid, which is initially 0.20, let me erase this for some room. This H+ is going to get fully used up, and then doing our limiting reagent chart, this is from stoichiometry, this is going to end up being 0, this is going to end up being 0.05, and this is going to end up being 0.30. And then you do your equilibrium calculation. So a cleaner way to do this is what we call an I-lyse chart, where we have our initials, and then we have our limiting reagent step, and then our ice chart. So starting off, we'll do the same exact thing that I just did, but in our I-lyse chart, where we have 0.10 here, and then this 0.10 is going to fully react and form a good bit of this. So now we have our new initial values, and now we could do the same exact process to find our new pH. So this is going to be minus x plus x plus x. So it's going to end up looking like this, and then Seneca bar equilibrium of 0.05x over 0.30 equals Ka, which is 1.8 times 10 to the negative 5. And then I could solve for x in our calculator, and x is about, with Sig Figs, 1.1 times 10 to the negative 4. And then pH will be negative log x, and that's about 3.97. So notice how our initial pH that we calculated was about 4.62, and our new pH after adding 0.10 molar of HCl is still about 4. So it's relatively in the same ballpark, and that's the whole point of a buffer. Now be careful, the one trick in a buffer is the AP could try to trick you, and in your limiting reagent step you could fully use up something. So let's add instead 0.20 molar of KOH, or basically OH-. So H- is going to react with the acid. So remember, adding a base would react with the acid, and adding an acid would react with the base. So now we're going to react with the acid, because we're adding a base. And this is going to form a conjugate base plus water. So we don't really care about the water, but we started off with 0.20, and we have 0.20 OH. Here we got 0.15. So doing our limiting reagent chart, we fully use up everything and only form acetate. So this will have 0.35, and this will have 0 and 0. So notice this is a trig buffer where now it's no longer a buffer solution, and now you only have CH3, so COO minus. So this is going to do hydrolysis, which we talked about in the last step of the video. So this is going to do hydrolysis and be a little bit basic. So be careful, the AP might throw a trick question where they fully use up the buffer like this. And let's say instead the AP added like 0.25 molar of OH minus, and this was 0.25. Now you'd actually be, this would run out first, and then this will be 0.05. And now this, you have OH minus left over. So you don't even need to do the equilibrium. You already got some OH minus sitting there. So you could negative log that OH minus concentration, and you'll get a pretty dramatic shift in pH. So if you take the negative log of 0.05, you'll get 1.3. And remember, this is the POH because we took the negative log of OH minus. So 14 minus that would give me my pH, and that would give me 12.7. So huge change once our buffer got used up. So that's how to deal with buffers. I forgot to add the Henderson-Hasselbalch equations, a common shortcut. It's very nice. Just says the pH usually of a buffer equals pKa plus log of your conjugate base over acid. Or you could also switch this to POH, pKb plus log conjugate acid over base. pKa, all that is negative log of your Ka. So if you have your Ka in these concentrations, you can get the pH just like this. You don't even need to show work. For an F or Q, I would advise show work, especially if you had time, but this is perfectly okay if you just write Henderson-Hasselbalch and chuck it into that equation. So yeah, good luck. Next part, we'll talk about titrations and more.